Hi. Today we will use TensorFlow and Keras in order to detect retinal eye diseases. So basically we will download images, a lot of images that are categorized to 4 different classes. So 3 of them are diseases classes, images, like these sample images, and 1 is a normal retinal eye. So basically it will be a multi-class classification, and we would like to detect each of those 3 diseases out of 4 types of classes. So first of all, let's go to the Kaggle website and we will search for this text retinal OCT images. Here it is. As you can see, we have 3 types of diseases and 1 type of normal retinal images. And this dataset is divided to test, train, and validation, and each of the train is divided to 4 folders. This is, for example, the DME folder. It's a type of disease, and there is a Drusen folder, which is another type of disease, and this is the normal folder. So let's download the dataset. I will fast forward it, and I download the zips, extract it, and put it on a folder named OCT, Retinal OCT Images. As you can see, this is the train folder. These are the normal images, and I can jump to another folder, for example the Drusen, which is one type of retinal disease. For human, I believe that for me it's I don't understand these images, but probably some medical experts can understand these images. So let's give the deep learning those images, and let's learn it to detect the diseases. I will copy paste the dataset so it will be easy for you to download, and let's start coding the first Python program. Okay, let's import some Python libraries. We will use NumPy, and let's import more functions from the Keras environment. So we will import the sequential model and some layers functions like the convolutional 2D, the max pooling 2D, flatten, and dense. Let's also import the function image data generator, which help us to load the information from the folders and transform it to our needs. And we will also import the early stopping function. First of all, the training folder, a simple copy paste. Just don't forget to change the slashes. Next, the test path. We'll place it with the test. Next, the batch size. We will run it with the 32 images per batch, and now let's build our model. So it will be a sequential model, and the first layer would be a conv2D layer. It will be composed of 16 filters, and the kernel size would be 3 by 3, and activation is reload. It's a straightforward process, and our input shape would be 224 by 224 by 1. Please notice by 1, that means it's a grayscale, a black and white images, not a color images. Next, it will be a max pooling layer, and the next layer will be another convolutional layer, and it will be a little bigger, 32 filters, and of course another max pooling layer. The next layer, it will be the flattening process, a flattened layer, and the last one will be a dense layer which is composed of our 4 classes, and the activation is softmax, which is relevant for classification and categorical problem. So basically it's a very simple convolution model. Let's print the summary of our model just to double check our code. As you can see, it was verified with no errors, so we can continue. Now let's compile our model. Our loss function will be a categorical cross-entropy, and the optimizer will be Adam, and the matrix will be accuracy. A very simple model, as I said earlier, and a very straightforward process of compiling. Next, let's prepare and load our dataset from the disk. So we will use the image data generator function, and we rescale the images by normalize the images between 0 and 1. Basically, each image will have a value for between 0 and 255. So for the model, we will normalize it between 0 and 1. Next, we are loading the information from the folder. We will use the datagen.flow from directory, and we will send several arguments. The first one is the path for the train images, the target size, and the bed size, which is 32. And the color mode important, it's a grayscale images, and the class mode is categorical. As I mentioned earlier, we have 4 classes, so it's a simple categorical question. And very important, shuffle through. That means that all the images on the train process will be shuffled. As for the test data, we are changing the path for the test images, and we don't need to shuffle the images. I believe all the rest should remain the same as the train. Okay, next process. Let's define our steps per epoch. That means we will define the amount of the samples, that means the amount of all train images by the bed size. And we will use the ceil function to round the result. Let's do the same for the validation images. So it's the amount of the test data divided by the bed size. Next, let's add an early stopping. We will monitor during the training process the validation accuracy, and we will look for a change by 5 epochs. That means if there was no change during 5 epochs, the training can be stopped. Now the Feit function is defining our last process, which is the training. So we will send several arguments, our train data, the steps per epochs, the amount of epochs we will train it on 50 epochs, then the validation steps, we defined it earlier, the validation data, which is our test images, test data, and the last one is the early stopping process. Okay, I think it seems okay. The syntax is okay, so we can now save our model. So after the training process will be finished or stopped by the early stopping, it will be stored in our disk with this name, Retinal oct.h5. Good. Now let's use the pyplot functions to show the results of the training. So we'll show it a diagram of the progress of the training and the validation training. So sorry, the accuracy and the validation accuracy for each of the epochs. So first of all, we have to extract the accuracy and the validation accuracy. We also extract the loss and the validation loss, and we will build two diagrams, one for the accuracy and one for the loss. So our x-axis will be the epoch. So let's create a range between 0 and let's say the last epochs, which is the length of the accuracy. If, for example, it will run through all the epochs, the value will be between 0 and 50, and if it was early stopped, it will be, of course, under 50. So first of all, let's plot the train accuracy. It will be with a red line, and now let's draw the validation accuracy. It will be with the blue line. This is the R and the B, and let's display the X label, which are the epochs, and the Y label, which are the accuracy. Basically, it will be two lines, one for the accuracy and one for the training and one for the validation. This would be the title, and we'll display the legends on the lower right position of the diagram. Now let's duplicate this code for the loss process. Let's display the loss and the validation loss as well. As you can see, I copy paste it, and now changing from accuracy to loss, and the text as well, the Y label and the title, and even the position of the legend. I think we are ready, and now we can start the training. So we can see we have about 83,000 images for training and about 1,000 images for testing. It's more like a validation. And now it's running the first epoch. I think I'd run it on a fast forward because it may take several hours. It depends on your GPU card. So let's go to the last process or the last epochs and see the results. Okay, the training is running. Let's wait a few more seconds. As you can see, during the training, the validation accuracy is about 0.9, which is a very good training and good validation accuracy. We are looking forward to see the diagrams. You can see a good correlation between the training and the validation accuracy. Let's see the loss. The loss is basically very good as well. Not a perfect one, but very good as well. So now we are ready to test our model with a fresh new image. As you can see, this is once again the validation accuracy, which the scoring is very good. Okay, let's go for the folder which the model was saved, and let's look for the file. Here it is. Very good, it was saved. So I believe that now we are ready to test our model. Let's create a new Python code. Let's call it step 2 test the model.py. Let's start with the import TensorFlow, import OS, let's load from the Keras utils the AMG to array and load image to load a fresh new image and convert it to a NumPy array. Let's also import NumPy and OpenCV. First of all, let's load our saved model. So we will use the load model function. Let's copy paste the folder, the path for our saved model. And next, let's print the summary just to double check that it was loaded correctly. We're expecting to see, for example, as last layer, our 4 categories. Good. Let's continue. Let's load our categories from the folder. Basically, let's create an array with the text names of those 4 categories. So let's copy the name of the folder, the validation folder. Let's change the direction of the slashes, and let's use the listdir in order to import the names of the folders into the categories variable. Let's sort it for ABC and let's print it. We're expecting to see 4 categories as we seen earlier. Let's also create another variable, which are the length of the categories. The value, of course, should be 4. Perfect. Now let's create a function that can load an image, convert it to a number array, and convert it to another number array, which is batches of images. These batches of images would contain only 1 image. So we are preparing this image for our model. So we will use the load image to load it from our disk, and we are converted to grayscale and to our target size, which is 224 by 224. Then we are converted it to number array, and then we are using the function. I have some syntax error, so I'm fixing it during the coding, but as you can see, I'm using the expand dims to create a batch of images. We are adding another dimension with the beginning of the number array. Then we are normalizing the image between 0 and 1 and returning this image, which is now ready for our model. Let's use one of the test images as our fresh new image. So let's choose, for example, this image. We will copy the name of the image and the full path. Once again, don't forget to change the direction of the slashes. Okay, this is the image. And now let's run our prepare image function that will return our prepared image for the model. Now we'll run the predict function and send in several arguments. One is our image, our converted image, and the next one is verbose 1. Then we are extracting the highest position of the highest prediction into answers, and let's print the answer variable. We're expecting to see a number, which is the position between 0 and 1. So as you can see, we got 0. That means that CNV is 0, DME is 1, Drusen is 2, and normal is 3. So 0 means that this image is a CNV disease. So let's display this text, this CNV text. So since we loaded these 4 categories into array, let's display the relevant array. Once again, let's run the same prediction, and now we are expecting to see the text CNV. Great. Next, let's show this image, and we will also display on the image this text as a one merge image and text. So we will use the imread in order to load our image. And let's choose one of the OpenCV fonts, and we will use the putText function in order to put our relevant text, the predicted text. 0 by 50 is the position. We also chosen any color. I think it's a purple color, and how thickness would be the text. Let's run it. I have a syntax error. Okay, I believe I forgot something. Let's fix it. Yes, of course, I forgot the font. Okay, let's run it again. Great, as you can see, this is the result. This is our fresh new image, which was predicted as a CNV disease. Let's try a different image. Now let's try this Drusen disease, this Drusen retinal disease. Let's replace our test image. So basically we are expecting to see the prediction of a Drusen disease with our new images. Let's run it. Thank you very much. I hope you enjoyed this tutorial as well. Bye bye.